So good afternoon, everyone. Last 4 days, we have discussed a few CSIR problems regarding with real analysis and linear algebra. Today, we are going to start with abstract algebra. In particular, we have to discuss about few group theory problems and a few concepts of group theory. So last 4 days are nice only. I felt somebody's there giving good feedback only from the response sheet. So I hope today also the session will going very smoothly. Anyway, I have to start that group theory problem, and again once more I will ask one request from the participant. If you have any doubt, please you have to send that message to the message box. So from that message box only I can understand whether you guys are understand or not. At least something I can realize. Okay. Anyway, fine. Today also going to solve only CSR problem, not for any other PhD entrance exam problems. So anyway, we have to start. The first problem, I have to start that class equations. The class equation is one of the important theory in the group theory place. Anyway, I have to start the class equation. Question number 1. Which of the following cannot be the class equation? Class equation of a group of order 10. Frequently asking regarding to group of order 10. Option A, 1 plus 1 plus 1 plus 2 plus 5 equal to 10. B, 1 plus 2 plus 3 plus 4 equal to 10. Option C, 1 plus 2 plus 2 plus 5 equal to 10. Option D, 1 plus 1 plus 2 plus 2 plus 2 plus 2 equal to 10. Please read the questions, then I will explain some theory about these class equations and we solve the problem. First read the problem, first try to understand which of the following cannot be the class equation of group of order 10. So given some random group whose order is 10, but we don't know the group. It could be abelian, it could be non-abelian. We don't know which is that group, but given order of G is 10, order of G is 10. We don't know which is the class equations. Option A, option B, option C, option D. We don't know. Still, we are not deciding. Is there any idea from the participant? Any guess? Any guess, please? Any guess, please? Any guess?
Option A is one of the guess, sir.
Oh, option A is one of the guess. Okay, very good, nice. What about B and C and D? Okay, anyway, I have to give the theory a little bit for theorems or some lemmas corollary. Then we have to try to solve. Without I am saying anything, you can able to solve. But instead of when you're going to solve, I have to give some theory about background of that class equations. And one more thing I want to say, in the CSIR examination, people who want to prepare this abstract algebra, you should follow this book. It's a very nice book. This book is name is Contemporary Abstract Algebra, Joseph Gallin. This is one of the main book for in the abstract algebra, and also it is very useful to qualify the CSIR exam. So why I am saying that this author giving a lot of exercise in the exercise book compared than other book. Actually, we are following here most probably University of Madras. So sustain book we are following. But in the exam point of view, this is a best book you should follow. It will help to qualify the exam very quickly. Anyway, fine. So I have to say about few theories about the class equation. Then you have to solve this problem. It is very easy only, not for difficult. Just I want to say that. Simple. Okay, just I will do it. First of all, C of A notation. What is that meaning? Set of all G in G such that AG equal to GA. What is that meaning? C of A means centralizer of A. You have to collect element which are commit with A only. Which are commit with A only. Just a collect element in G, they are commit with A only. That is notation of C of A. And next, CL of A. What is the notation of CL of A? X, A, X inverse such that X belongs to G. This is a very shortest notation. Or otherwise, we can write set of all B, or you can write some other notation set of all B in G, A equal to or B equal to X, A, X inverse for some X. For some X in G. So instead of B, just written here X, A, X inverse, just X in G. That's all. This is a CL of A, class of A. Okay, fine. Again, I would like to write two theorems, then you have to solve these problems. Very easy only. No need proof. Just to know the concept, then you can apply. So theorem number 1, let G be a finite group. Let G be a finite group, and let A be an element of G, then order of CL of A equal to order of G mod C of A. Index of G mod C of A. Or if you write order of C of A instead of, you can write index, order of the index. This is a theorem number 1. Another one more theorem. In a finite group, I will explain, don't worry. In a finite group, order of CL of A should divide order of G. Another class equation. This is important for class equation. For any finite group, or any finite group G, order of G equal to summation, right, like order of CL of A. Order of G index C of A, or summation of order of CL of A. Order of CL of A, where A in G. That's all. Where A in G. I think this is enough to solve this problem. Now here, so C of A, CL of A is given meaning. What is the theorem says that let G be a finite group and A be any element of G, then order of CL of A from the conclusion, I would like to write here, order of CL of A equal to order of G index C of A. Right, this is nothing but order of G mod C of A. Then this is nothing but order of G by order of C of A. right? This implies that order of C of A, or you should, this implies that order of CL of A should divide order of G. From the theorem, they can conclude this theorem. Order of CL of A is nothing but, so the thing is that CL of A means A is conjugate to B if there exists X in G such that B equal to XA X inverse. Conjugate element A is conjugate to B. A is conjugate to B means there exists some element in G as this property. How we can say A is similar to B matrix, given A matrix and B matrix there, how we have to say A is similar to B? If there exists some invertible matrix P such that A equal to P, B, B inverse. P, B, P inverse. The same thing happens here. So A is conjugate to B means there is some element with the acting X, A, X inverse, which implies B. Then we have to say that an A, B are conjugate. So here we are collecting set of elements. CL of A means which are element which are conjugate to A. Suppose I am here, CL of me. CL of me is nothing but who are all conjugating with me. I collect all those elements. That is CL of me. CL of you means who are all conjugate with you. Collect all those elements. That is called conjugate of you. CL of u. The same thing, just there is an element A and B are conjugate means at least there is some element, at least one element in G which are conjugate to B. Conjugate in the sense B equal to X, X inverse. That's all. Okay, fine. That is the meaning of CL of A. So here this theorem says that G any finite group, A is any element, you have to find the CL of A. The order of CL of A is nothing but order of G index of C or G mod C of A. Just we can write order of CL of A equal to order of G mod C of A. From this conclusion, you have to bring this side, you bring this side, which implies that order of CL of A should divide order of G. Point number 1. This theorem over. From that theorem, we can conclude order of CL of A should divide order of G. Now, what is that? This is a class equation. This is a class equation. This is a class equation. What the class equation says that given any finite group G, whose order of G equal to sum of summation where A belongs to J, order of CL of A, running all the elements of A in G. For example, just I would like to explain, not example, I would like to explain what is that meaning. Suppose G is the set A1, A2, A3, A4, and so on. Now, only 4 elements are there in G. Then order of G equal to order of CL of A1 plus order of CL of A2 plus order of CL of A3 plus order of CL of A4. That's all. We don't know how many elements are there. We don't know how many elements are there. When you sum, suppose this is a 5 element, this is a 4 element, this is a 6 element, this is 7 element. We don't know. We can sum all the elements which is equal to order of G. But it could be repeating. It could be repeating in the sense order of CL of A may be 4 na. Order of CL of A3 also 4. We don't know. This it could be 2 or maybe 3 or again 3 or 2. We don't know what is it. We can't predict any number. But this theorem says that order of G implies that order of CL of A. Order of CL of. Now I would like to ask question. Participant, be ready. G is a group. Finite group only. Just we are asking that. You know center of G definition, right? Center of G means this is a notation of center of G. What is that meaning? Set of all G in G. such that AG equal to GA for every A in G. What is the meaning of center of G? Center of G is nothing but you have to collect an element in G. That element commute with every element in G. Center of G means center of G is a subset in the group G. How the element look like in the center of G? If an element belongs to center of G, the element should have property. What property? The element should have this property. What is that property? AG equal to GA for every AG, which means if an element belongs to center of G, that element should commute with all the elements in the group. C of A means commute with only A only. Commute with, just I am putting here. Collect element, commute with only A. Here, Z of G. You have to collect element, commute with all this element. That is called center of G. That is called center of G. Now, I would like to suppose you can assume that this is a center. A belongs to center of G. A belongs to center of G. Now, what are the elements which commute with A? Or I can ask question, what is your CLFE? This is a theory. You know the theory, this problem is very simple. So most probably you go on the PhD entrance, in the abstract algebra, they will be asking from class equations. Not only PhD entrance, our CSIR exam also having class equation, and the class equations are the main important part in group theory. And also most probably they will be asking NGHM questions and CMA, other IIT entrance, they will be asking this class equation. That is why I am trying to explain at least a little amount of theory, not for a large number of theory, just a few theory concept only I try to explain here. Okay, anyway, fine. A belongs to center of G. What is the CL of A? Someone answered. I didn't see that. What is that answer, please? Participant, anyone?
It is the identity element and inverse of A. Somebody has replied.
Wow, nice. So the same person I would like to ask the question, what is the cardinality of CL of A if A in G? A in center of G. A in center of G. Just where I am writing here we have to concentrate, develop your mathematical logic. Here I am asking CL of A. Then here I wrote already what is the meaning of CL of A? X A X inverse such that X in G. What happens if you write like that? What happens if you write like that? X A X inverse such that X in G. See here. See. Now A is in center of G. If A is center of G, what happens? A commute with every element. Don't confuse here. Just I here written G. Or I would like to write here B. Class of B. Class of B. B belongs to center of G. Now what happens? B is in the center, which means B commute with every element. If you commit B here, now B commute with every element, what happens? What happens, please? B commute with the X, B X inverse. Why? B is in center. Center means is commute with every element. In particular, commute with X also. Now I would like X B X inverse such that X in G. Now what happens? X inverse, what happens? Is identity. So this implies that B only. What is the moral of the story? Someone, I asked the question, what are the numbers in the CL of A when A belongs to center of G? Someone they said identity and A inverse. That is not true. That's false. See here, CL of B is nothing but X B X inverse such that X in G. B in center. Center means it commute with every element in G. In particular, it commute with X also. So XB X inverse, instead of I can write B X inverse. When X inverse are identity, just you are correcting B only. What is the moral of the story? What is the moral of the story? I would like to write here, if X belongs or B belongs to center of G if and only if CL of element in the center, when the element in the center, which are element conjugate to with that element is itself only. What is the moral of the story? If here I written here, if B belongs to center of G, if and only if CL of A equal to B only. Now, what is the class of B? Order of class of B. This implies that order of CL of B equal to 1 if and only if B belongs to center of G. Please note it. If element in center, then the corresponding CL of B is B only. Order of CL of B is nothing but 1 only. Only one element which are conjugate with B only. That element itself only. Okay. Are you okay with? Okay. Now I have tried here. I would like to ask some questions, please. It is giving interest. Don't worry. Okay. Order of center of G equal to summation order of CL of A. This is a class equation. A in the G. Suppose this is a G. This is your center. I would like to write center A1, A2 and A3. Only 3 elements. Now here I would like to rewrite this equation. Order of CL of A1, order of CL of A2 plus order of CL of A3 plus and summation A does not belongs to center of G or A does not belongs to center of G. A belongs to G. A belongs to G but does not belongs to center of G. Then you can write order of CL of A. So if A1, A2, A3 are in the center, now what is the cardinality of order of CL of A1, order of CL of A2, order of CL of A3? How many elements are there? One element. Very good.
Element, sir.
One element. Very good. Good. So now this equation becomes 1 plus 1 plus 1 plus again we don't know remaining class of A. We don't know remaining class of A. Is an element in G, but A does not belong to center of G. Why? Already center element we are calculating. So that is why we are avoiding here overlapping. So now order of CL of A. Okay. What is the moral of the story? How many elements are there in the center? How many elements are there in the center? That many ones are coming here. Here our center 1 plus 1. Here our center contains 3 elements. Therefore, we written here 1 plus 1 plus 1. Remaining we don't know. And also we are concluded here. If B is an element of center of G, order of CL of A is 1 only. Why? If an element in the center, 4 element conjugate with that element is only itself only. Okay, we are proved and explained here. So very clear. If what I am going to say, if an element in center whose corresponding order of CL of E is 1 only. If a group G is a group, if center has a 5 element, then corresponding class equation is 1 plus 1 plus 1 plus 1 plus 1 plus remaining we don't know. And whose sum is order of G. Remaining we don't know, whose sum is order of G. Are you okay? Are you okay?
Yes, sir.
Okay. Okay. Another one more question I will ask. Okay. Now, one of guy, he is attending from Delhi. That guy name I don't know, Vikram Sharma. Come on, response me. Come on. If G is abelian, finite abelian group. G is abelian, okay, and order of G equal to K, then then what is the class equation? Then what is the class equation of G? So just I written here order of G equal to how it will be the class equation? How is the class equation? If G is a finite abelian group, we are defining class equation only for finite groups. Class equation for any finite, only finite group, not for infinite group. So that is not meaning, because it will be order G equal to some finite number of values. It could not be infinity like that. Okay, anyway, fine. G is abelian group and order of G equal to K. What is the structure of the class equation? Naveen. Okay, very good, Naveen. Excellent. Naveen, answer that question. Whatever I asked, he is answering. Thank you, Naveen. He is explained. I understand why. Here G is abelian means the class equation is Naveen giving answer 1 plus 1 plus 1 plus on so on 1 k times why why it will be k times 1 1? How he is guessed? Remaining people just think.
Sir, one second. There is a question from the participant. How to find how many elements are there in the center of a group?
Oh, that is not easy. But how to find a center means this is the notation for center. Center of G equal to given any arbitrary group. From that arbitrary group, what are the elements satisfying this condition? Collect those elements. That's all. It depends the group. It depends the group. We can find a center. This is a general method. This is a set notation. Given G, given group, they are given group. You take one element, this element commit with all the element or not. If commit with all the element, then I can take it. I conclude this belongs to in the center. Again, I will take remaining element in the group. I will take random element in the group. I have to check it will commit with all the elements or not. If it commit all the elements, then it will put in the center. I collect the element. This is a set notation. There is no general method for if a given group order of G 1 to 20, then what is the center of G? We don't know. We can't say. If order of G equal to 100, what is the center of G? We can't say. Only thing is that this is the notation for finding center. This is the definition of center. You can apply. It depends the group we can find. Otherwise, we can't. Given random group of order 1000, then what is the center of G? Now we don't know. Whether that group is abelian, non-abelian, we don't know anything. Okay, anyway, nice question. So, is there any question, madam?
No, sir, not so far.
Okay, madam. Now, I would like to ask another one more question. It will be interesting. G is abelian. What is the center of G means? Naveen giving the answer 1 plus 1 plus 1 plus and so on is given. So, why this happens? Once you know all those things, once you know this theory, minimum theory only you know, then answer is it's very simple. You only going to right now take it. I'm not doing anything. Come on. So just I am giving a tool to solve that problem. I am making tool. Okay. If G is abelian, what is the meaning of abelian? G is abelian means Abelian means xy equal to yx for every x comma y in G. Any element in G, they are commute. Then we say that that group is G is abelian. Okay. Now suppose A is there, A is conjugate to B. What is that meaning in? What is that meaning? There exists x in G such that B equal to x A x inverse. Given parents group is abelian, what happens? What happens? What happens? What is the CL of A? What is the CL of A? A in the abelian group. CL of A notation means x A x inverse, right? Such that x in G. Just to see the notation. A is an element in the abelian group, therefore A commute with every element. In particular, A commute with x also. Now what is this? What is this? X inverse such that x belongs. What happens? X inverse going to identity. Now only remaining A only. You are wearing x inverse, it will be identity. Identity A and identity A only. So given only A only. What is the moral of the story? If G is an abelian group, you take any element in G whose order of CL of A is nothing but whose order of CL of A is only 1 only. Whose order of CL of A is 1 only. Why? Just I wrote that the class equation definition. A element in G, this A commute with every element. Why? G is abelian group. My parent set is abelian group. So A commute with every element. A commute with every element. A x inverse, it becomes A only. Oh, now what is the moral of the story? If an element in the abelian group corresponding whose order of CL of A is 1 only. Here with G is any general finite group. If it's an element in the center whose order of CL of A is 1 only. Whose order of CL of A is 1 only if A is in center. Similar same concept here. Here center means it commute with every element. Here the whole group commute. Take any two element, it will commute. Okay. So you take any element in the abelian group whose order of CL of A is 1 only. Now what is the class equation? Class equation is nothing but order of G equal to summation of order of CL of A. So G is abelian, each order of CL of A is 1 only. So order of G equal to 1 plus 1 plus 1 plus 1 plus how many elements are there in the G? That many ones we have written 1 plus 1 plus 1 plus 1 plus. Suppose order of G equal to K, how many ones are there? 1 plus 1 plus 1 plus up to K times we could write. Did you getting my point? Did you getting my point? Okay. So I would like to one question here. Okay. Order of G equal to 6 and G is abelian. G is abelian. Which of the following are class equation? Which of the following are class equation of G? I will write here. 1 plus 1 plus 2 plus 2 plus equal to 6. 1 plus 1 plus 1 plus 1 plus 2 equal to 6. 1 plus 1 plus 1 plus 1 plus 1 plus 1. Which is the correct one? Order of G 6. Order of G 6.
Option
Okay.
C, sir.
Option C. Very good. Order of G 6. G abelian. Which are the following class equation in the sense? Here we are conclude that theory. If G is abelian group, you take any element whose CL of A is only single element. Therefore, order of CL of A is order of CL of A equal to 1 only. If an element in the abelian group whose corresponding order of CL of A is 1 only. So order of G, and finally whose sum equal to order of summation order of CL of A is equal to order of G. So here was R of G is 6. So number of element in R of G is 6. So this is not class equation. Why? Why? This says that only two element G is abelian group. So G is abelian group. Each class equation cardinality is one only. Here it will be 2. It's not possible. Here also 2. It is not possible. So therefore this is not a class equation. What about this? G is abelian. Every class equation of cardinality is one only. But here okay, here okay, here okay. But what about last? This is not okay. Even though we are summing 6. 1 plus 1 plus 1 plus 1, 4 plus 2, 6. Even though sum is 6, but it is not a class equation of order 6. And finally, 1 plus 1 plus 1 plus up to 6 times we have written 1 and this is equal to 6. Okay, sum is 6 as well as G is abelian. Each class equation cardinality is 1 only. Each coordinate of class equation 1. So how many elements are there? 6 elements are there in the group. You take order of CL of A1 plus order of CL of A2 plus and so on order of CL of A6. Each order of CL of A1 1 only. Okay, so that is why I written here 1 plus 1 plus 1. This is a exact class equation of order. Only general. In general, any abelian group, G is an abelian group, then whose class equation is 1 plus 1. Just I written here general theory. Okay. Yeah, here I written here. If G is any abelian group, order of G equal to K, then the class equation structure is 1 plus 1 plus 1 plus 1 up to K times. This is a general class equation of abelian groups. Abelian groups. Abelian groups. Okay.
Sir, one minute. There's a participant whose response is that all the elements will be in the center of the group if the group is abelian.
Very good. It's a nice question. Yeah. This is a very nice question. This is another one. It's a very simple only. What the question they asked? G is abelian if and only if center of G equal to G. Actually, if G is abelian means xy equal to yx for all x and y. It's a commute with every element. You take any two elements, they are commute. That is abelian. Instead of you are going to say abelian, you have to say these things. You take any element in the center, which is an element of G. We have to prove that center of G equal to G. So two sets are equal. How we have to prove? This is a theorem statement. This is a standard statement, and the result. Lot of books are there in the abstract algebra. But anyway, I would like to say a few hint. So this is a set. We have to prove these things. G is abelian if and only whose center equal to G. So how we have to prove two sets are equal? This is a one set and this is another one more set. Center of G is a set. How we are collecting here? Center of G is a collecting element in G only. Clearly, center of G is a subset of G. One side, okay. What about this side? You take element which is in the center. How to prove? This is very clear. Why? Center of G is a subset. Center of G is by notation. We are collecting element in the G. So therefore, center of G is a subset of G. So clearly, this one very obvious. What about this? If you take element in the G, you take an element in the G, which is an element in center of G. Assume that. You have to assume this. You have to prove this. You have to assume. Why? Because we have to assume this. This is abelian group. You have to prove. If you have these things, then you have to prove abelian. Okay. Now we are assuming abelian. We have to prove these things. Once abelian implies center equal to G. So you take element in G. What is that element? You take element in Y. What is the property? What is the property that? Let just you take element. Let Y in G. What happens? Y commit to let Y belongs to G. This implies that xy equal to yx for all x in G. Why? Since G is abelian. Since G is abelian, which implies Y commit with every element which belongs to Y belongs to center of G. Right? Just take a random element Y and G is abelian. Using abelian property, xy equal to yx for all x in G. For all x in G. For all x in G. So y commit with all the element, which implies y belongs to center of G. So you take any arbitrary element which is an element of center of G. Therefore, two sets are equal. If you assume that G is abelian, we are proved center of G equal to G. Is it okay, madam?
Yes, sir. So we can conclude, if it is an abelian group, the class equation will be of the form 1 plus 1 plus 1 till the number of times order of G.
Very good, very good. Excellent.
We can
madam.
conclude.
That is our conclusion.
Okay, sir. Thank you.
Okay.
Sir.
Another one more question they asked. No, G is abelian if and only if, instead of saying abelian, you have to say center of G equal to G.
Yes, sir.
I proved only one side. I am assume G is abelian, then I proved center equal to whole G. Every element in the G is center. That is the meaning. Abelian, every element in the center. G is abelian, every element in the center. The converse also, G is an arbitrary group. I have a center. The center equal to whole G, which implies that G is abelian. The converse part I am asking. Center and the whole G are same, which implies that abelian. So obvious. Why? So obvious. Why? Abelian means what do you want to say? Abelian.
It commutes.
You take random two elements, whether they are commute or not. To take two random elements and given hypothesis center of G equal to G, two elements are in center. Center element means commute with every element. In particular, commute with this Y also. You getting my point?
Yes, sir. Yes, sir.
You take two elements. Actually, we are going to prove this side. Take two elements. We have to prove G is abelian. G is abelian instead of we have to say just to take two elements in the G. Suppose they are committed, then we have to conclude that G is abelian. Just randomly I take two elements. There's two elements in the G, which implies that two elements are in the center of G also. If an element is center of G, commute with every element. In particular, this element commute with this element also. Every element in the center commute with every G. In particular, commute with this Y also. Therefore, X and Y are commute, which implies that G is abelian. This is a if and only. Very simple, easy proof only this theorem. Anyway, you understood. Okay, anyway, fine. We are concluded G abelian and center of G equal to G. Is there any question, madam?
No, sir.
No more question. We will proceed that problem. Okay. So, okay. Now, I would like to ask first thing. Group of order of G10. Given any class equation become abelian groups of order 10. So given 4 class equations given. I don't know whether the class equations are or not. I don't know. I'm asking question. Any group of order, any abelian group of order 10, any one of them is class equation? Very good, excellent. Those people are there, understood very clearly. Because madam also said, G is abelian, the class equation structure is 1 plus 1 plus 1 plus 1 only. So no class equation here 1 plus 1 plus 1 plus 1. Okay, therefore, the 4 equations given, they are none of them class equation of finite abelian group of order 10. Then nothing equation becomes an finite abelian group of order 10. Maybe it could be non-abelian group of class equation. Maybe we don't know still, but we are assured that order of G10 and G is abelian. Nothing of them class equation. Okay, this is the one conclusion. Okay, come on. Okay, and also here I said that here is an element. Suppose when we write class equation, how many ones are there? That many elements in the center. I written here 3 elements in the center. The class equations of the form 1 plus 1 plus 1 plus remaining we don't know. We can't conclude. Still we don't know. But how many elements are there in the center? That many ones are coming. That we will give surety. Okay. Fine. And also, we know that center of G is a subset of G. Not only subset, it's a subgroup. It's a subgroup. Not only subset, it's a subgroup. G is a finite group. G is a finite group. Now, what do you know about G is a finite group and order of G and order of subgroup? What do you know about? Is there any theorem linked? Is there any theorem? G is a finite group and Z of C is a subgroup. Is there any connection with subgroup and order of that group? Right? Very good. Lagrange's theorem. Very good. Super. Lagrange's theorem says that order of G, order of center of G, or subgroup should divide order of the group. Order of any subgroup. Order of center of G. Center of G is a subgroup should divide order of G. Center is a subgroup whose cardinal should divide order of the coordinate. Good. Very good. Nice. Okay. Now, from that conclusion, how many, suppose G is a random group whose class equation written, someone written, they said this is a class equation. Then suddenly they asking question, how many elements are there in the center? Just I will write here, order of center of G equal to some K, order of center of G equal to 1 plus 1 plus 1 plus, we don't know, some L1 plus L2 plus and so on, some LR. Some LR equal to K. Now my question. Order of G equal to K, random group whose order is K. Now, what is the means order of the center of G? We don't know. Just they say that. Come on, someone written. So good, very good, Naveen, very good. Order of G is K. Order of G is K. And the question asking how many elements are there in the center? The answer is 3. Why? I told that when you write the class equation 1 plus 1, that many elements in the center of G. Here 1 plus 1 plus 1 3 times I written here. So from the, suppose this is a class equation of G, this implies that order of center of G equal to 3. How many ones are there when they write the class equation? That many elements exactly precisely in the center of G. Are you okay? Is it clear?
Sir. Yes, sir.
Okay. Okay. Now we have to move the problem. Okay. Now what is our conclusion? Here they said that precisely center of G is a subgroup and G is a finite group. By Lagrange's theorem, order of the subgroup should divide order of the group, which implies that order of center of G should divide order of G. Okay. Suppose this is a class equation of a group of order 10, which implies that how many elements are there in the center?
3.
3 elements are there. It's correct, right? 3 elements are there. We know that the center is a subgroup. By Lagrange's theorem, order of center of G should divide order of G. Suppose this is a class equation of some group of order 10, this 3 should divide 10. Is it correct, madam?
It's not possible, sir.
This is not possible. 3 does not divide 10. So therefore, this is not a class equation of any group of order 10.
Yes.
Okay. Fine. Okay. This is not a class equation. They are asking cannot be the class equation. So this is not. Suppose this is a class equation whose center contains 3 elements. Center is a subgroup and the subgroup contains 3 elements. The 3 should divide 10. This is not possible. Therefore, this is not a class equation. So Our question is, which are the following not a class equation? Cannot be the class equation. This is not a class equation. What about this, madam? Come on, madam. Someone please.
Here the
B.
center of G will be one element. So that one can divide 10. It can be.
It can be, we are not sure, right?
Yes. It can be.
But the suppose this is a class equation of group G of order 10. Center contains precisely one element. Center contains precisely one element. But this is some CL of A, some CL order of CL of A, some order of CL of B, some order of CL of C. First, you have to sum. It will be whether it is a 10 or not. 3 plus 4, 7, 7 plus 2, 9, 9, 1, 10. The sum is correct. Another one more thing written here, from that here, order of CL of A should divide order of G. Just to see the notes. See the notes. Right? Order of CL of A should divide order of G. I somewhere written, I think I rub it. Just to see the notes.
You wrote in the beginning.
Yeah, we wrote in the beginning. Order of CL of A should divide order of C of A.
So in that
This is
three
clear
cannot,
for this.
Three
Yeah,
cannot
this is
divide 10.
yes, madam. Very clear, madam. This we have to check another one more thing. Now the center we can't conclude. Center divides. Number of elements center divide. We can't suppose center of number of elements center should divide in the 10. We can't say that this is a class equation, or we can say that this is a class equation. We can't conclude anything. But 2 divide 10, but 3 order of CL of A, each order of CL of A should divide 10, but this is not possible. 3 does not divide, 4 does not divide. Therefore, this is any group of order 10 cannot be class equation. So this is not possible. Okay, this is not possible in the sense this is our answer. Okay. Now what about this, madam?
This can be possible, sir.
This can be possible. If it is possible means we are to try to give, there is a group of order 10 whose class equation is this. If it is possible means we have to give on a group whose class equation is this. Otherwise we can't accept. Anyway, we will come after sometimes. Option C. What about D, madam?
So it will have a center of order 2.
Yes.
That
Yes.
will divide order of G.
Very good. Very good. And 2, everything order of CL of A also divides, and sum also 10. Everything it will be supporting. But it will be supporting. We can't conclude that this is a class equation. Is it correct?
Yes, sir.
We can't conclude. Okay. Anyway, I am trying to give an example. G is finite group, and let G is a finite group. Suppose G mod center of G is cyclic. This implies that G is abelian. This is a G mod center theorem. G mod center theorem. I think in the group theory, only 20, 30 theorems, lemmas, it is enough to understand the group theory. Anyway, fine. G be an arbitrary finite group, and the center they are given. Center they are given. G mod center of G. This is a quotient group. Whose quotient group is cyclic, that group should be abelian. This is a theorem. G is arbitrary finite group. There someone gives center. Unfortunately, G mod center of G is cyclic. Then that arbitrary group is abelian. This says that. This is a theorem. G mod center theorem. G mod center of G is cyclic, which implies that then G is abelian. It implies means then G is abelian. Okay, fine. Suppose now conclude center containing 2 element. Center containing 2 element. G mod order of G mod center of G. What is your conclusion? This is equal to order of G by order of center of G. 10 by 2. This is equal to 5. Another one more result. Just write order of G equal to P. This implies that order of G equal to P, which implies that G is cyclic. Cyclic, which implies that G is abelian. A group is cyclic, which implies G is abelian. This implies that G is abelian. This no, everybody know. Who are all studied in abstract algebra, everybody know. Now, center of G is not a subgroup. When we write quotient group, the subgroup should be normal. Otherwise, we can't write quotient group becomes this. Not we can't. We are creating only quotient group. How we are creating? If H is a normal subgroup, then G mod H is a quotient group. The H should be normal. Here, center is a subgroup, we know. And another one more things also there. Center not only subgroup, it is a normal subgroup. Therefore, we can able to define G mod center of G. Okay, anyway, fine. This is a quotient group. This quotient group's cardinality is 5. So quotient group is cardinality is P. Any group of order prime, then G is abelian. Here, any group of order prime, then G is abelian. Now the quotient group of order is 5, which implies that the quotient group is abelian. According to any group of order 5 prime, it's cyclic. The quotient group G mod center of G is whose order is 5 and 5 is a prime number. G mod center of G is a cyclic. Cyclic implies abelian. Once G is abelian, the class equation does not have center 2. Did you getting my point or getting confusing? Just I am using this theorem. Suppose this is a class equation of some group of order 10. From that things, G mod center is cyclic. According to this theorem, G mod center is cyclic, which implies that G is abelian. So parents group is abelian. Once the parents group is abelian, the center can't be 2 element. Okay, madam?
Yes, sir.
Is there any doubt? So therefore, option D is cannot be any group of order 10. Any group of order 10. So therefore, this is not a class equation. Sorry, this is not a class equation means they will be asking not a class equation. What about this? I'm not going to explain. It will take time. So this is a D5. This is a class equation of D5. The D5 center contains only one element identity and 2 reflection. Totally in Dn, how they are defining Dn? N rotation, N reflections. N rotation, N reflections. And there is a separate theory how we are writing a class equation for Dn. There is a very big theory, not very big theory, it will take more than 1 hour. And when we write Dn, the class equation is when n is even and when is odd, there is a different stories there. But right now I am going to say that this is a class equation of D5. I'm not going to prove right now. This is a class equation of D5, which means some group of order 10, it will be a class equation. Okay, anyway, fine. Now the question, what are the answer? Option A, B, and D. This is the correct answer. Is there any question from this class equations? Are you okay, madam?
Yes, sir. So far, no questions from any participants.
Okay, ma. I hope class equation most probably they can realize right now. Now you have to answering anywhere they will be asking class equation. You have to first think about center and think about order of CL of A and do sum. And you can use some theorems like this kind of theorem. We don't know, not exactly giving perfect, but some option they are giving some little difficult. Okay, anyway, fine. So I was explained very slowly. I'm very sorry. I will move fast, little bit fast for some other problems. So don't worry. Anyway, fine. It's a very simple question. Another one more question. If x comma y comma z are elements of a group such that x, y, z equal to 1, then this is a 4.75 mark, I think so. Very simple question only. Y, z, x equal to 1. B, y, x, z equal to 1. C, z, x, y equal to 1. D, z, y, x equal to 1. What is your answer? Please come on. First read the question. Someone option B, C. What is it meaning first of all? G is a random group. G is a random group. Yes. There is an element x, y, z. There is an element x here, maybe y here, z here. This three element having some property. What is that property? X, y, z equal to 1. Maybe x, y inverse, maybe z, or y, z inverse x. We don't know. Or y, z x, maybe we don't know. Just there is an element in the group, three element x, y, z, random three element x. That element is called x and y, z. What is the property as? X, y, z equal to 1. As this property. Then whenever x, y, z equal to 1, which implies that y, z, x equal to 1, y, x, z equal to 1, z, x, y equal to 1, z, y, x equal to 1. Did you understand? G is a infinite, finite, we don't know. Just a random group. There is a three element as this property. What property? X, y, z equal to x, y, z equal to 1. The three element having this property, which implies then the same three element has this property, this property, this property, and this property. How to conclude? I think getting an idea very clear. Okay, anyway, I will try. Not try, we will do it. X, y, z equal to 1. X, y, z equal to 1. Now, I multiply x inverse on both sides. So x inverse is identity, then becomes y, z equal to x inverse. Now I multiply this side the x. Y, z, x equal to x inverse x is equal to 1 only. Identity. Here the this 1 means identity. Or instead of 1 they can put e. It's okay only. Why they are not giving e? Everything element x, y, z in the variable alphabets. If you put the e, they are confusing. So that is why they are avoiding e and they put 1. Anyway, so y, z, x. From this, bring it y, z, x. Y, z, x. Whenever as this property, from that things imply this. Is there anything similarly you can find, please? I will do it one side, one property from that things I bring it. Try to do it. C also, nice. Is it nice? Okay, we can check. From the things, from y, z, x equal to 1, we can bring maybe, is there any other property? Just I multiply y inverse on both sides. Then z, it becomes identity. Identity means 1. Z, x equal to y inverse. Now I multiply y on both sides. Z, x, y equal to 1. It's nice, right? So it It will bring here and also here. So Z, X, Y. So what about remaining? Check. This is homework for you. This is homework for you. From this, whether we can bring it, the two things. Just to see.
No, sir.
See.
It's
No,
not possible.
It's not possible. Very good, madam. This is not possible. So whenever an arbitrary group has this property, which always implies that A and C. The answer is A and C only. Is there any question? Okay. Okay. Now we'll go some other. Actually, group theory, sometimes they will be asking very simple question only. But nowadays they will be asking involving number theory, the congruence. Nowadays they will be asking including number theory with algebra. Another one more easy problem. Okay. Okay. A group G is generated by the elements X, Y with the relation X cube Y square XY whole square equal to 1, then the order of G is 4, 6, C, 8, D, 12. What is the meaning? Please. It's an easy problem only. The class equation only take more time because there is a lot of background of theories there, and also so in the PhD entrance, most of the place they will be asking for in the class equations, and in the interview panel also they will be asking class equations, and they will be asking why you want to study class equation, what is the importance for in the group theory of class equations. Suppose if we write a class equation G, what implies that? So more questions are there. Okay, whenever you have free time, just you can read. Okay, option B and C. B, sir. Okay. Anyway, I explained. G is an arbitrary group. The group generated by, what is a generator? Group G is generated by elements X and Y. X and Y only generating the group, which means any combination, not a combination here. You take X and Y, from the XY only produce all the elements. You take random element some R, the R produced by X and Y only. Some X power 10 or Y power 5, both the things gathered and giving R, maybe. We don't know. That is the generator. Given any group, given any element in the group, that element produced by with the two elements multiplying or which means binary operating, both of them are one only binary operating, or rising power X power some K star Y power some S, which implies that element, it could be, we don't know. So anyway, I will write here G equal to X Y such that X cube equal to 1 and Y square equal to 1, XY whole square equal to 1. This is our relation. We take element XY and the group generated by two element, and the two element has this property. What property? The first X element, X cube equal to 1 and Y square equal to 1, XY whole square equal to 1. So when we know these things, xy whole square, xy whole square, xy equal to 1. So, and also you can rewrite x, this is equal to y inverse. So from that conclusion, y square equal to 1 implies y equal to y inverse, right? It's an element of order 2. Y equal to y inverse. Just I am pre-multiplying, post-multiplying y inverse, it becomes x equal to y inverse, or xy equal to y inverse x, and y equal to y inverse y x inverse. So many way of relation they will be asking. Maybe next time they will be asking, instead of this, they would ask xy equal to y x inverse, or xy equal to y inverse x inverse, or xy x equal to y inverse. They will be asking different, the same relation, they will be asking different way of mannering. Okay, anyway, I will write Dn set of all R and S such that R power n equal to 1, S square equal to 1, RS whole square equal to 1. This is representation of Dn. Dn, this is one of the way to representing the Dn. So exactly they are giving some Dn. Okay. So R is a rotation, S is a reflection. So Dn they are created by n rotation, n reflection. So rotation has this property and reflection has this property. So reflection of order 2. Suppose this element is there, rotating 2 times, it will be original position is coming. It will be identity. So rotation means it will be n times it will be rotating. So inside polygon, from that inside polygon, we can make a Dn. But anyway, that will be very big theory. We don't have time to explain that thing. But this is a representation of Dn. Now you can conclude that here R and S, they will be giving x and y. So you should write in the x and y format, x and y. You can write xn and y. That's all. X, y. This is a rotation and reflection. Now see the relation. See the relation. From that things, x cube equal to 1. So therefore that G equal to D3. So order of D3, order of Dn equal to 2n. From that things, order of D3 equal to 2n. 2 into 3 means 6 elements. 3 rotation, 3 reflection. From that thing, just to take a triangle, this is a triangle, equilateral triangle. So this is one reflection. This is another reflection. This is another reflection. And 3 rotation. Each rotation 120, 240, 360. So 3 reflection, 3 rotation forms D3. So 3 reflection, 3 rotation, totally 6 element. So order of Dn equal to 2n, which implies that order of D3 equal to 6. So the cardinality of this so the answer is B only. D3 contains 6 element. D3 contains 6 element. Is there any question? A simple only. This is not very big. Just a representation only there. So you should write this representation. Here also they will be asking some different kind of mannering. They will be asking a relation. That's all. So here x, y equal to y into x inverse. Instead of x power n minus 1, they will be asking some other value. X power x minus 1 equal to x power n minus 1. Here from the things they will be substituting some other things. Be careful. Okay. Anyway, fine. Madam, is there any question, madam? No.
No, sir. No question.
Okay, madam. Okay, madam. I will cover more questions in few minutes. Okay. So what is the fourth question or fifth question? I don't know. Okay. What is the cardinality? Cardinality of the set of all Z and C complex plane Z power 98 equal to 1 and Z power n not equal to 1 for any n lies between less than 98. A equal to 0, B equal to 12, and C equal to 42, and D equal to 49. First, see what is that meaning. Please read the question. Read the question. Hindu, someone answering Hindu. Good. I don't know that answer, but she tried very quickly. What is the cardinality of the set? First, what is the meaning of that? C star, C is a complex plane. Okay. They are collecting element in the complex number. The element has this property. Element has this property. What is that meaning? Z for 98 equal to 1. Then what is that meaning? Z power n equal to 1 means they are collecting nth root of unity. Generally, right? Set of all Z in C, Z power n equal to 1 means they are collecting nth root of unity. Here our n is 98. So 98 root of unity they are collecting. They are collecting. Also that not collecting for all the element. The number before the 98, the number should not be 1. The number should not be 1. For example, so 1 satisfying this condition. On 1, this does not satisfying this condition. For all n, Z for n equal to 1, 1. So 1 is not in the element. Okay. For example, just I will be explain Z power C, Z power 4 equal to 1 and Z power n not equal to 1 for any n less than 4. Suppose 1 satisfying this condition, 1 does not satisfying this condition. Okay. Minus 1 satisfies this condition and minus 1 not satisfied this condition. Why? When n equal to 2, minus 1 whole power n equal to 1. Okay. So they are collecting element Z power 98 1 before is never getting 1. 97, Z power 96 not equal to 1. Z power 30 not equal to 1. You take any number between 0 to below 98, which means up to 97, the Z never become equal to 1. Never Z power n become 1. Okay. So I try to explain. Suppose this is a 98th root of unity. 98th root of unity. 1 they are giving. So which means that 1 is there in the complex plane. 1 is there. This is an unit circle. So element you take modulus, it becomes 1 only. So when the collecting elements, another one more information that the elements lying in the unit circle only. Why? When you take that element, just to take modulus, it becomes 1 only. So they are collecting in the unit circle. Fine. And also 90th root unity. They are not collecting all 90th root of unity. So 90th root of unity in the sense, just I will try to draw here. Suppose 4th root of unity. What is that? Where it will be lying? So 1 I minus 1 minus I. It become like spire, right? Okay. Cube root of unity means and 1 the omega and that omega square. That will be 1 and here and somewhere here, somewhere. This will be a triangle. And z power 5 equal to 1 means 5th root of unity. The nth root of unity means the unit circle n equal parts they will be cutting. They start from, suppose the arc is k meter, k length. This is also another k length, another k length, another k length. How many k length? N k length. Okay. Nth root of unity, each one they are lying. So first root here, second root here, third root here, fourth root here, fifth root, and so on. All n roots are lying in the unit circle. They have the same equal distance for it. Take any two, not any two. Consecutively you take two. Just this is the length of k. This is also length of k. The length of k, which means the unit circle we have to cut equal distance or equal piece of length k. It has n pieces. Given 2 pi r length, no, 2r, 2 pi r radius 1, no, 2 pi length of the boundary of the circle. We have to cut n equal parts. The first cutting is 1 and remaining you have to equally divide and cutting. So each cut of the end, the unit circle roots, so the nth root of unity roots lying in the each part, each place, here and here and here and here and so on. They are collecting in the complex plane and 98th root of unity. This is basically a group, 98. So we know very clearly nth root of unity form a group, not a group, it's a cyclic group. It's a cyclic group. And from that nth root of unity, they will be restricting some restriction. So without asking anything, suppose this is what is the cardinality of these things, then 98. Why? It's a polynomial of degree. Just think about this. 98 minus 1. This is 0. This is an equation. This is a polynomial of degree 98. How many roots are there? 98 roots are there. Is it correct? Okay. They are collecting 98 roots. But given among the 98 roots, some roots are they are violating. Some elements are violating. What is that meaning? Here I written here 4. No, how many elements are there? We are concluding this. 1 is not there. 1 satisfying this condition. 1 does not satisfying this condition. 1 is not there. What about I? I satisfying this condition. I power 4 equal to 1. I square minus 1. I cube not 1. Up I satisfying this condition. I belongs to. What about minus I? Minus I is satisfying this condition. What about minus I? Minus I is the same. So, and minus I also there. Only 2 elements are there. Actually, the fourth root of unity 1 minus 1 IA minus I. 4 elements are there. So here when we restricted, instead of 98, if I restricted 4, only 2 elements are there. Okay, they are restricting. So instead of 4, you write 98. How many elements are there? One more point. This is a group and 2 elements are generator. The generator only, I told that nth root of unity form a cyclic subgroup. I'm not going to prove, right? It's a very simple only. Nth root of unity form a cyclic subgroups in C star. Basically, this is a cyclic subgroups. 98th root of cyclic groups of order 98. Of order 98, how many elements has this property? Which means how many generators are there? Group of order 98. Group of order 98. This is a cyclic subgroup. So if order of G, if G is a cyclic group, order of G equal to n, then how many generators are there? You know very well in the group theory, right? Just I would like to write here. Order of G equal to n. G is cyclic. Then number of generator of G is what? Is what? R of G equal to n and G is cyclic, pi of n. Janani, very good Janani, very good, excellent. Pi of n generators are there. Janani, okay. So pi of n generators are there. Do you know find the pi of n means? Pi of n is nothing but so the number which is less than n, which is relatively prime to n. So number of element which are relatively prime to n. Number of n, number of element which are relatively prime to n. That is a pi of n. So is there any formula for pi of n? Yeah, there is some formula in pi of n. How to find such a pi of n formula? Just I will write here. Suppose given any n, I can write product of prime power alpha. P1 power alpha 1, P2 power alpha 2, and so on, some Pk power alpha k. Now the pi of n is, pi of number of relative prime is nothing but n into 1 minus P1, 1 minus P2, and so on, 1 minus Pk. This is a formula for finding this is Euler phi function. So pi of n is giving counting for number of element which is less than and also relatively prime to n. So instead of pi of n, you can write this. This is a pi of n formula. Okay, this is a generator. Now using this, used here, how many elements are there? Come on, this is a 98, which means pi of 98. First 92, 98. How to write 92? 98 equal to 49 into 2. 7 square into 2, right? Correct. So now what is the pi of 98? 7 square into 2. That is n, right? N. Instead of n, just I write n. Into 1 by 7 into, doesn't matter the power, doesn't matter of the power here. 1 by 1 by 2, 1 minus 1 by 2, right here. This will be 6 by 7 and 1 by 2. 7 and 7s are cancelled and 2 are cancelled. 7 into 6. 7 46 42. 7 into 6 42. So is there any answer? Oh, this is the answer. Okay. Someone already said this answer. Very good. Anyway, thank you. So answer is 42. Is there any question? Is there any question? No. Okay. Okay. We will go. Isomorphism. Hello.
Yes, sir.
Oh, suddenly there will be mic is not working, madam.
I think there is some network issues. Now it's working, sir.
Okay, madam. Suddenly they said that it's a recording process. That's all. They stopped, and when I go and see the mobile, it will be mic is muted. Okay. Anyway, this is some technical issue. No problem. Up to isomorphism, the number of abelian groups of order 108 is what? Is 12, 9, 6, is 5. What is the answer? First of all, what is the question? What is the question? What is the question? Up to isomorphism. Up to isomorphism, number of abelian groups of order 108 is what? Any answer? Any answer? Any answer? A only. Aha. A na 12. Okay. Do you know the isomorphism? Up to isomorphism? Do you know the up to isomorphism? What is the meaning of up to isomorphism? Okay. Someone they said that yes, sir, I know. Okay. I try to explain what is the meaning of up to isomorphism. First, G is a group. Only we are going to talk about finite groups only. Okay. Finite group only. Just assume that order of G equal to K. Order of G equal. The question. First of all, how many groups are there? Somebody's written. What the madam? Someone written? What the
After prime factorization of 168, use the
Ah.
partition of 2, 3, 2 and 3.
Okay, I got it. But they are saying how to find number of groups they said. But anyway, I have to say the theory. Then we have to solve this after that. Okay, I would like to explain what up to isomerism. First, we know up to isomerism. Otherwise, we can't conclude what is the meaning. Okay, anyway, order of G equal to K. This is some finite group of order G, so of order K. The question: how many groups are there in the world of order K? First question. We don't know how many groups are there. We know maybe million groups are there, or it could be infinite number of groups are there, or it could be finite number of groups are there. We don't know. It's a random group of order K. For example, 5 order. How many groups are there? We know is that 5. Maybe is there some other group? Is there some other group? Lot of groups are there. We don't know. So it could be finite, infinite. We don't know. But there are groups of order K only. Isomorphism means, suppose this is a G1 group, G2 group, G3 group, and so on. Some GR group. Each group of cardinality K only. Each group of cardinality K only. Now, up to isomorphism means, if you take any group of order K, some GS, which is isomorphic to some groups of the order K. The question is, I will be saying very simple way. Non-isomorphic number of non-isomorphic groups of order K, that is called up to isomorphism. There is a order of G equal to K. There is a some group order of G equal to K, but both the groups order K, but they could be isomorphic or non-isomorphic. We don't know. If it is non-isomorphic, then we can counting. So non-isomorphic means up to isomorphism. Maybe 100 groups are there of order K. Just assume that. Among the 100 groups, only you take any 100 groups in between. Let us assume that you take any group among the 100 groups of order K. Take any group, some G, Y. This group is isomorphic. This or this or this. Suppose up to isomorphism of order K, only 3 groups. You take any K order group which is isomorphic. This or this or this. Only 3. Many groups are there. Order of G equal to K. So among such group, you take any group which is isomorphic. Some groups among lot of groups are there now, among few groups. For example, this class, 100 people are there. Just let us assume that we have 5% they are standing. You take any guy in the class, that guy having any one of them property. You take random any guy in the class, that guy has the property which is isomorphic to me or this guy or this guy and this guy or any one of the 5. If this happens for in the class, we are up to isomorphism only 5 only. Which means you take any guy which has the property among any one of the 5. So we don't want to conclude all those people. We are studying only for non-isomorphic. But in the we are 5 people are there, no? Here. Each of them non-isomorphic. And me and this guy are non-isomorphic. And each of them are non-isomorphic. You take any element, take any group of order K, which is isomorphic to me or this guy and that guy, that guy. Up to isomorphic means lot of groups are there of order K. Among lot of groups, among the groups, we try to collect a few groups. The few groups are each of them non-isomorphic to each other. So how many non-isomorphic groups are there of order K? That is up to isomorphism. Which means how many groups are there of order 108 which are non-isomorphic to each other? Which are non-isomorphic to each other? That is the question. In particular, abelian groups. They are asking up to isomorphism, number of abelian groups of order 108. Of order K, abelian groups are there, non-abelian groups are there, lot of abelian, lot of non-abelian there. But here our question is only for abelians. How many abelian groups are there of order 108 up to isomorphism? Suppose 108 order 5 groups are there. Someone bring it. Someone bring. Sir, I have group of order 108. That group, it could be isomorphic to this or this or this. To take any group in the world of order 198, which is abelian, that group is isomorphic. Some we are collecting few groups that will be isomorphic. Some groups of the few groups. Okay. The question is how to find a number of few groups. These few groups having property, each of them non-isomorphic. Each of them non-isomorphic. There is a formula for to find if order of G equal to some n, order of G equal to some n equal to P1 power alpha 1, P2 power alpha 2, and so on, PR power alpha, product of prime. Every number can be written as a product of prime, product of some prime powers. Number of, and assume that G is abelian. G is abelian group and order of G equal to n, and n can be written as this, then number of non-isomorphic groups of order n is partition of alpha 1, partition of alpha 2, and so on, partition of alpha r. Start to product. Now the question is, what is the P of alpha 1 meaning? What is the P of alpha 2, and so on. So here the number of non-isomorphic groups of order n is, instead of the number of non-isomorphic, means they will be asking the same equivalent meaning up to isomerism. Up to isomerism. So here they will be asking up to isomerism, means number of non-isomorphic groups of order n is pi of the P of alpha 1, P of alpha 2, and so on, P of alpha. Now question is, what is the P of alpha 1, P of alpha 2, and P of alpha? Partition of suppose partition of 1, partition of 2, partition of 3. 1, how we can split it? 1 only. 2, how we can split it? 2 and 1 plus 1. 3, how we can split and write it? 3, 1 plus 2, 1 plus 1 plus 1 only. Okay, partition of 1 only. Partition of 2, 2. Partition of 3 is 3. What about partition of 4? 4, 1 plus 3, 1 plus
1 plus 1 plus
2,
1 is
2, very good. 1 plus 1 plus 1 plus 1. Is there any other thing? 2 plus 2, right?
Yes, sir.
And 2 plus 2 plus 2. So this one counting 1, 2, 3, 4, 5. So this is a 5. So we can write like, there is no general formula for P of alpha. P of n. There is no general formula for to find P of n. We have to remember P of 4 is 5. P of 6 is, P of 5 is, I think, 7. P of, just we can do it. P of 5 is 7 and P of 6 is, I think, 11. And P of 7 is, I don't know, remaining things. I just remembering only few things. Anyway, fine. So this is a formula, P of alpha. Just you know, for alpha, no, then you can conclude like that things. Now the question is 108. 108, how to write here? 54 into 2. Yes. 54. 3 square into 3 into 2 into 2, right? I am very weak for this calculation. 3 power 3 into 4. Okay, very good. So 2 square. Now you have to calculate here. You have to calculate P of alpha, no? P of alpha 1 to P of alpha 2 alpha. Alpha 1 is in 3, alpha 2 is 2. P of 3 into P of 2. P of 3 is nothing but 3 and P of 2 is 2. 6. So 6, right? Yes, correct. 6 only, right? It's correct. Yeah, 3 power 3 into 2 power 2, 27 into 4 is 108, correct only. And P of 3 into P of 2. P of 3 is 3 only, P of 2 is 2. So therefore 6. The answer is 6. Is there any question? Is there any question?
No question, sir.
Okay, madam. So I think last before CSIR they asked the same, just they will changing something similar only. What is that question? Same up to isomerism. They are not mentioning, I believe. Just I will write it. It will be easy only. Another question. The total number of non-isomorphic groups of order 122 is option A 2, option B 1, option C 6, option D 4. And what is the answer? That will be one CSR question. This is another CSR. Next year CSR question. Now the total number of non-isomorphic groups of order 122. Here we are written only for abelian. Assume that G is abelian, order of G equal to n then. So 1 sir, no, this is not a abelian group. They will be asking 120 order abelian also there, non-abelian also there. Don't calculate for only for abelian. They are not mentioning for abelian. Abelian also there, non-abelian also there in the world. We don't know. Calculate, please. Is anyone answering? The total number of non-isomeric groups of order. First, try to find 120 order for abelian. 120 order. 122 order group, abelian, non-abelian. But we know up to isomorphism bar, for abelians. What is the formula? What is the formula for abelian? What is the formula for non-abelian?
P of 2 into P of 61, sir.
P of good. 122, I can write 61 into 2, right? Yes. 61 is a prime and 2 is also prime and alpha is 1 and 2 power also 1. So abelian group P of 1 into P of 1. 61 prime, 2 also prime. So power 1, power 1. So alpha 1 is also 1, alpha 2 also 1. So P of 1 is 1, 1 into 1, it will be 1 only. So number of abelian groups up to isomorphism of order 122 is 1. So lot of abelian groups are there of order 122, but all those abelian groups which are isomorphic to only one group. What is that group? Z122. You take any group of order 122 abelian group which is isomorphic this Z122. Z122. Take any group. So up to isomorphic only one groups are there. Suppose there is a group whose order, there is abelian group whose order is 122, which is isomorphic to this. So number of up to isomorphism group is only one group up to isomorphism. Lot of groups are there, but each group they are isomorphic. But we are calculating non-isomorphic only. So according to that formula, we have only one group. That is in particular, we have to say 122. Nothing wrong. Okay. Now we have to think about non-abelian group. We have to think about non-abelian. The question is, how many non-abelian groups are there? Okay. There is no general formula for a non-abelian group, but some non-abelian group of order this, then we can conclude that so unique non-abelian group are infinitely many. We can conclude we have some result. I will try to write here. If order of G equal to PQ, P less than Q, P comma Q are distinct primes. Distinct primes. So here means distinct, but still written here distinct primes, prime number. If P divides Q minus 1, then there exists unique. This is a symbol for unique. Then there exists a unique abelian, non-abelian groups. There exists, if P divides Q minus 1, then there exists a unique abelian group and unique non-abelian group. Only two groups are there. Any groups are there. Abelian also, lot of groups are there. All those groups are isomorphic with this. There is a many non-abelian groups are there. That non-abelian group is isomorphic with this. That is what this theorem says, that if order of G equal to PQ, P divides Q minus 1, then there exists a unique non-abelian group and unique abelian group. Only two groups are there. One is abelian. One is abelian means ZPQ. Non-abelian means DPQ. DPQ, that's all. Point number 1. Point number 2. If P does not divide Q minus 1, then there exists a unique cyclic groups. There is a unique cyclic groups. Cyclic implies abelian, which means there is only unique abelian groups only. P does not divide Q minus 1, then there is a unique cyclic groups of order this, of order PQ. Unique cyclic groups. Cyclic implies abelian. So there is a unique abelian groups. Okay. Now come here. 122, we are written here 61 into 2, 2 into 61, P into Q, 2 divides 61 minus 1. 2 divides 61 minus 1, which means 60. 2 divides 60. Go here, P divides Q minus 1, then there is a unique abelian group, unique non-abelian group. How many groups are there? Only two groups are there. One is abelian, another one is non-abelian. So abelian we are calculating through this way, 1 only. So non-abelian also 1 only. So totally two groups are there in the world of order 122. Groups are there, lot of groups are there, but that group is isomorphic to this non-abelian group or this abelian group. That's all. Okay. So number of non-isomorphic groups of order is 2 only. 2 only. Is there any question?
No question, sir.
No question. Madam, what is the time?
So almost time, sir. It's 4:57.
4:57. Okay, 3 minutes are there. Okay. So again, some question. The number of group homomorphism from Z10 to Z20 is 0, 1, 5, 10. So I would like to give the general theorem. Zn to Zm. Number of homomorphism. Number of homomorphism, just a homomorphism called phi, is GCD of n comma n. This is the formula. Now the answer is number of group homomorphisms. They are asking how many group homomorphisms are there? Z10 to Z20. How many groups? According to this standard result, and GCD of 10 and 20 implies number of group homomorphisms, and GCD of 10 and 20 implies 10 only. So the answer is 10 only. So I would give one homework for you. Number of onto homomorphism. Just they are asking here only for number of group homomorphism. Same thing. Now the remaining question, the homework, number of onto homomorphism for this. The answer is number of onto homomorphism 0. Why? It's a 10 element, this is a 20 element, there is no onto map. 0 only. But here they will be asking number of homomorphism. The answer is 10 when we calculate in GCD. Now the question is, now this is a general formula. From the things I would like to ask question onto. And onto, when we write onto, and m is always less than or equal to n. Another one more condition, n greater than or equal to n. Now number of onto homomorphism. Number of onto homomorphism. How many onto homomorphism are there? Please try to go and check this whatever net or book, or you can try to construct. That will be maybe coming next CSIR exam, or you go to somewhere PhD entrance exam. They will be asking number of onto homomorphism. But here number of onto homomorphism 0. But here I will give conditions n Zn to Zm and n greater than or equal to m. The number of onto homomorphism is not GCD of mn. There is some condition is there. There is some condition. You try to fill that condition. Okay. Anyway, I think the time is run out. Thank you for listening and passioning for sitting and hearing whatever I am explaining. Thank you. Madam, is there any question? You want to say something?
No, sir, there is no questions.
Okay. You want to finish the session, or I can
Yes, sir.
continue?
Yeah, we can wind up, sir. It's
Okay,
5
madam.
o'clock. now.
Okay. Yeah.
Participants, any question, you can post it in the chat box. Okay, sir, I think there is no questions. There are no questions in the chat box. Thank you so much, sir, for sharing broader concept of abstract algebra and explained us very clearly. We have learned new techniques on how to solve the problems. Thank you once again for sharing your knowledge, sir. I request all the participants to fill the feedback form that has been posted in the chat box. Hope today's session also would have helped all the participants in acquiring new information. Keep practicing and be ready for tomorrow's session sharp by 3 p.m. Thank you, everyone.
Thank you, madam. Thank you. Thank you.
Thank you, sir.
Okay, madam.